just a couple other things as well. There are other sort of things that are on the table that you'll learn as you go through that are different. So you have metals, metalloids, and gases. So metals are essentially just pure metals, such as aluminium, such as copper, such as steel, such as iron. These are pure, steel's technically not pure, so steel's not a bad example, don't listen to that one, but iron. These are pure metals. Pure metals that are shiny, they're malleable, so that means I can hit it really hard with a hammer and it'll just bend. So think about it if you've seen those, like, it's also a bad example because they're slightly different, but think of like, you've probably watched a movie or a TV show where they've used, not ancient, they're at like, the Camelot times, so like the knighthood times, and they're getting their swords and they're dipping it in the cauldron and they're hitting them with a hammer, they're pulling them out of the fire. Notice how they don't shatter. That's because they're malleable. They can bend, they can change. Think of it like that. Ductility refers to the ability to make a wire out of metal. So all of our wires in all of our machinery, it's metal, it's ductility. They're silvery. They have a high boiling point and melting point. They're really good electron conductors, which means, or electrical conductors, which means that they can conduct electricity, which is why we make them into wires in the first place, because they move our charge and therefore we have electricity movement. They're also really good heat conductors. What's a really good example of that? Pots and pans. Your pots and pans move electricity through, so that's also one thing that makes them really good. Metalloids, on the other hand, these have some metallic and some non-metallic properties. So some metalloids can be ductile, but also be colored, so they're not like silvery and shiny. Others are a little bit different. These are metalloids. You will learn which of these are metalloids in the periodic table, don't stress. Gases, these are essentially dull. They're not malleable, they're not ductile, they can be colorful. They usually have a really low boiling point and melting point, that's why they exist as gases. But if you did cool them down to a really, really cold temperature, far enough down that you ended up with, your sort of solid, you'd find that they're not good electrical conductors, they're bad heat conductors, they're not ductile. You'd find they don't have any of those properties. Now, the groups that we discussed before, your alkyl earth metals, these have a low melting point and boiling point. They're soft, they have a high density, and they're highly reactive. Now, we'll talk about our Gs in a bit, so don't worry about that. Transition metals, everything's different, so don't worry too much about it, but they have metallic properties, but it's really dependent on the element as to how strong those metallic properties are. Your halogens, these are gases at sort of STP, which is just room temperature, if you like to think of it like that. They exist in pairs of atoms, and they're reactive and they're colorful. So I want to talk about halogens very quickly. Halogens here are these molecules here. So halogens exist as pairs because they share their last electron. Now, we will discuss this in a little bit more detail, but essentially, elements want to have a full electron shell. They want to share. They want to share their last electron. They want to end up with a full electron shell. Now, a full electron shell for most of all of these will be 8. So especially these first two, they will be 8, and they've each got 7 because they're in the 17th group. This one will just have 2 shells. This one will have 3 shells because it's in the 3rd period. So being in the 3rd period and being in the 17th group, it has 7 in its outer shell. It's got 3 shells. Its outer shell has 7. It wants 8. So it will pair an electron with another chlorine. So essentially what it will do is it'll share one of its electrons, in a sense, to sort of share one back. So it gets sort of one back. Essentially what that means is you end up with this idea that with one of these electrons being shared, you sort of end up with 2. So you get one shared there, one shared there. So you end up with these shared sort of pairings, and you end up with this idea that you end up with an extra electron. So this is Cl2 in a sense. You get F2, etc., so forth like that. Now, apologies, we're still transitioning color. It's because I'm doing this at like 9 o'clock at night, and my computer goes into that blue light thing, the yellow light, non-blue light thing. So you probably just saw that there. I apologize for that. Nonetheless, going back. Your noble gases exist as singular atoms. Now, this is really important. Now, I need to go back again. Now, these are because these already have a full outer shell. So why would I share anything? If I've got everything I want, why would I share? That is precisely what is happening here. So these don't share anything because they've already got a full outer shell. They don't want to do anything. They're pretty stable. They want to do what they want to do. So essentially that's what goes on there. So that's what you need to know from each of those sort of groupings.